And I'll share my screen. We are looking for screen 2 is what it says. Does everybody see my my mouse?
Yes.
Okay, good. I'm gonna, if anyone doesn't want to talk in the mic, I have the chat open as well. So if you want to ask questions or say something, I'll be able to see it. All right. So both exams seem to have CRC on there. So I guess a couple quick points for CRC that are important to know is you can see he'll give you a message in bits and he'll just tell you this stuff, and then he'll give you this in polynomial format. So in this case, you got to expand this out, you got to turn it into bits. So that's the first complicating factor that might trip some people up. So what is it? This is +1. So in the 0th place or the least significant bit, you'd have a 1. And then that's 0th power. First power is X, and that's a 1. So that's another 1. And then into the second is not here. So that means it's a 0. And then we reach the 0, 1, 2, 3 is technically this one, right? 1 or 0, 1, 2, 3. Yeah. So this one has a 1. So it's this. This should be the message, or this should be the generator polynomial extracted from the actual polynomial in binary form. So that's the first complicating factor. So as long as you can pull that off correctly, then the rest of it should be relatively simple, because doing this is really easy. Just do 1, 1, 1. Then you draw the funny bar, and then you have your message. That is meant to be 0. Easy. Now, I mentioned this to a couple of people who were here beforehand, but contrary to like normal division, I never put anything on top of the bar because functionally it's useless for this. It doesn't make any sense. So I just leave that blank and I just go down and get the remainder because that's all they're looking for. So then this one's a really quick one because it's 1, 0, 1, 1 bar. So these are all going to be 0, 0, 0, 0, but you don't even have to write those because the exclusive OR operation, if they're the same, they just stay 0. This is going to be a 1. You carry down this. And then you also got to carry down this, and then you have to tag on a 0 to carry it down to make it 4 long. So now we have a message of 1, 0, 1, 0. Then we add our generator back on. Do this again, 0, 0, 0, all the same. Oh, look, we have a 1, so that's still 1. And then we have to tag on a 0 and tag on a 0 to drag it down. Thinking this, we tag on 2 zeros to finish it off. And this would be the answer. So this is the transmitted code word. And why, another question that's important to ask is, why is it 3 long? You ask, why did I not tag on 4 zeros? Why did I tag on any zeros at all? This is dictated by the leading highest order polynomial. So if you have 3, it means your tag on at the end, your remainder should be the same length as your highest order polynomial. So in this case, we had a remainder of 1. I had to tag on 2 extra zeros to make it 3 long. So that's just that. So now we have that. That means our transmitted code word is simply what we started with, plus tag on these 3 digits on the end, 1, 0, 0. So this was our message, and this is our code word. And this whole thing is the answer to part A. Any questions there? Everyone get that? No? Yeah. These are pretty quick. Like, honestly, the hardest possible thing is just if the message gets longer or the polynomial gets longer. Beyond that, I don't think these are all that tricky. So now I have to go into mouse mode to drag stuff down. There we go. That, okay. Do that. There we go. So I go down here and it says, suppose node B receives the following code word here. So you sent the code word and then we go annotate again. So now we received, draw your bar, 1, 1, 0, 1, 1, 1, 0, 1, 0, 0, 0, 1. And then of course, mutually agreed upon between these nodes is the same generator polynomial. So we put 1, 1, 1 as our divisor. I don't remember the vocab for that. And then you do it again, and you need to confirm that you get the exact same response here. Or more accurately, you need to confirm that you get the need to confirm that you get 0. Someone messaged me. Bonk, bonk, bonk. All right. Can everyone still hear me? Making sure that nothing's going wrong.
I can hear you still.
Okay, good. Yeah. So now what we need to do is this is the transmitted message. See, this says receives the following code word. So what we're looking for here is not the same CRC result of 1, 0, 0. It is, you're looking for all zeros. You want a remainder of 0 because that means the message is unaltered. There we go. So in this case, we just do the same procedure we did there. We tack on ours. Did I write this wrong? No, I did it right. Yeah. So we do that. And the generator is the same. Yeah, all right, good. So we can do this now. So now we do 0. We have a 1 here now. We have a 1 here now. We have a 0 here now. We can drag down a 0. Now we have a 0. Then we go 1, 0, 1, 1. And then we do this now. So that's 0 because it's the same. 1 here, 1 here, 1 here. Drag down a 0. Then we do 1, 0, 1, 1. Another line. Same here. That's a 0. 1 here because of the different. 0 here. 1 here. Drag down another 0. Now we're at this. Put our generator. Do this again, same, 1, drag this down. We have a 1. Well, we already have a problem here because we have a remainder. So there was an error here. So we did in fact detect bit errors. So you would literally, the answer for this would be circle this, say remainder, found bit errors. So we need a retransmission. Do that. And mouse mode. All right. Now down over to some short answer questions. So we have, what is the difference between connection oriented and connectionless? So connection oriented means that it has a connection beforehand. It is before transmission is completely aware of the transmission path. So that normally entails handshaking beforehand to understand where you're sending your data. And then a connectionless service, it does not know. It depends on routers to handle everything for it functionally. And it's going to depend on some type of routing system. It has no clue where its data is going. In fact, each frame of data it sends could go a completely different path. It has no clue what's going on. So that's just the main difference between these two services. That's an easy 2 points. Exposed node problem is best explained, sorry, by a quick little doodle. So if we have node A, we have node B, and we have node C. And let's say that node A's range just clips B, and node C range just clips B. And let's say that A is communicating with B here. And let's say that because of how 802.11 works, A sends out a request to transmit, or request to send, B accepts it, and then mutes the network. Well, here's the problem. C is within range of B. So let's say C was trying to communicate with some faraway node D over here. C does not care what's going on over here. And yet, since C is still within range of B, if B transmits the jamming frequency to free up A for transmission to prevent any collisions, C will be affected by B, which will result in C being forced to stay silent and not being able to communicate with D during the duration of communication between these parties. So that's the exposed node. The source or his answer is a node whose transmission has no interference to other nodes is forced to keep silent. So you could write it that way, and that's probably how he wants to since it's a short answer problem. But just to keep it straight in your head, this little figure is this covers how it actually behaves. Any questions on that one real quick? Nothing, all right, clear drawing. Go down to the mouse. So now we have Manchester stuff, dual time. So for Manchester encoding, it is the center is where your bit is caught at. So you take the center of each wave peak. So if you're extracting timing information and given the binary data, so he just wants you to extract ones and zeros here. So you draw these lines. your dotted lines at these little dots here. Because that's where the data will be found. So Manchester operates as follows. You'll have a rise for a 0 and a fall for a 1. That's how this goes. So if we look here, what happened here between this period? This is where the bit happens within these. So I should specify here, these dotted lines I drew, between the dotted lines is where you're looking. You're looking for what transition occurs within the time unit, within the dotted lines frame. So if you look in the first one, a fall happens. What does that occur to? That's a 1. Next timing increment, we have a rise, that is 0. Then we go to the next timing increment, we have a fall, that's a 1. Next timing increment is a fall again, that is a 1. Then we go on to the next timing increment, which is a rise, that's a 0. Next timing increment is another rise, that's a 0. And the next timing increment is a fall, that's a 1. Next timing increment, rise, that's a 0. So our message is 10110010. That's all that takes for part C of that. Then part D is suppose a receiver gets a chunk of HDLC formatted bit sequence, and then it gives you a big old bit sequence here, and then you got to perform bit destuffing. So I believe bit destuffing is cutting out the zeros. Destuffing. So in this instance, it would just be taking out this, this, and this. This 0 goes. So that should just be that's 5, another 5, 0, another 5, and then 0. That's the bit destuffing process, where you just cut out the zeros to make these contiguous ones. Because what this means is during the sending procedure, because this is the receiver getting it, doing bit stuffing is ensuring that there's never going to be more than 5 contiguous ones, right? So the transmitter inserts these zeros to ensure that there's never 5 contiguous ones, because if there were, then you'd have a problem, because I believe that's a special character reserved in HDLC formatting. So you had to do this, which means on the receiver side, which is where we're looking at this problem from, you have to perform bit destuffing, which is actually pull the relevant data, because the zeros that were inserted are not useful zeros. So you just pull the first 0 between every bit sequence. And that should be that. And then the last one is 2 communicating devices are using a single bit even parity check for error detection. Transmitter sends this and receiver gets this. So it asks if you get the error. So we just look at this, we count the ones. 1, 2, 3, 4. So first message had 4 ones and it's even. So we're looking good there. And now we check here, 1, 2, 3, 4. Second message also has 4 even. Look at the messages are the same. They are not. First byte here, or first 4 bits is 1001, and this one's 1010. So these, while they are both even and have 4 ones, they are not the same, which means there was a transmission error, which means the receiver misses the error if it's using single bit parity, single bit even parity. So it will not detect it. So explanation wise, you would just write down that original message has an even number of ones, received message has a even number of ones, therefore the receiver cannot detect the error. So that's all you got to do there. Mouse mode. So this particular thing where we're doing learning bridge stuff, it was TED that we are not doing that since we did not reach it. So we skipped question, what was that, 3? I'm going to do question 4. Yeah, block. I need to draw. There we go. All right, math time. So most of the trouble with this class really just comes down to units. As long as your units end up straight at the end, it means you probably did it correctly. So you can use units as somewhat of a sanity check to make sure you're doing everything right. So we look at this. So we need to extract information. So first things first, let's use our bandwidth on the total of network, right? propagation delay between any two hosts is given as 20 microseconds, and it's happily labeled for us here, so we get a little visual. And then the frame to transmit from node A to B consists of 1,000 bits, so that's going to give us, our frame size, so we can actually calculate the speed. And then each switch could start retransmission of a frame 10 microseconds after receiving the last bit of a frame. So that's important. So you got to collect the whole frame before you retransmit it, which means the whole frame has to get through the link and be received by the switch before it can begin retransmission. So all that really does is implement a 10 microsecond delay in the system. So then you have to say, what is the time necessary to transmit the data as a single frame from A to B? Time from first bit of frame transmitted by node A until last bit is received. So we'd have time should be equal. First, we're going to need the bandwidth of the links. So we have the size, which is 1,000 bits is our frame, divided by bandwidth, which is 10. Now in reality, that's better written as 10 times 10 to the 6th, but I'll just keep it unit wise here. And we'll do this bits up here. Then from there, what is this actually giving us information on? This is giving us the information on the bandwidth of each of these links. So you got to do this times 3 plus the next unit here, which is this 20 microsecond delay times 3. So we do 20 microseconds times 3 here. So this is the bandwidth delay. This is the microsecond delay just built into the links. So this could be based on like the length of the link, something like that. And then the last thing is the delay implemented by the switches, which is a 10 microsecond per switch. So that's going to be plus 20 microseconds total. That's 10 microseconds times 2. That looks like a milliseconds, microseconds, whatever. So doing the math on all of this should yield us, this is going to be 60 microseconds plus 20 microseconds. So now we have 80 over here. And this is 1,000, 1,000. So this should just be 1,000 at the end. No, should be this should result in milliseconds. So that's 300 microseconds or 100 microseconds. Then times 3 produces 300 microseconds. So this is 300 microseconds. Sum these up. Your result is 380 microseconds for this transmission to occur in total. Any questions on that? Any questions as to why we consider both the propagation delay due to most likely length or other factors and the bandwidth factor, or is that all pretty self-explanatory? Make sense? All right, good. We will go into clear all drawings mode and go back to the mouse mode. And then we have to calculate throughput here, data rate. So what is the effective data throughput rate for this one frame A to B in bits per second for the network as analyzed? So rate is just going to be equal to our frame size divided by our speed of transmission, which is 380 microseconds, written explicitly as 380 times 10 to the negative 6 seconds. Doing this math is just going to be 2.63 megabits per second. So as I mentioned, got to get your units, right? Bits, seconds, bits per second. And in this case, because it's 1,000, you could write this as 1 megabit. Checkmate, you see? That's how you can use units to sanity check yourself to make sure everything's going right. So whenever you see bits per second, you're probably going to want to make sure your numerator works out to be a bit value in some way, and you're going to want to make sure your denominator works out to be seconds in some way. Yeah, all right, clear, and mouse. So this is ARQ. So this should be the drawing the funny lines. Yeah, love it. All right. Mouse mode. So actually, let's go back here. So this is going to have a lot of information in it. So you're going to want to make sure to really like read it very deeply. I'd recommend a highlighter or at least circling stuff that's important. So you have a first thing first. Your window size is 3. That's very important. That means you're only sending in bricks of 3 before you receive an acknowledgement. Then frames are sequenced using infinite numbers. So this is just goes on forever, so on, frame 1, 2, 3, 4, blah, 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 blah up there, right? And then we have seek num to ACK is the pointer that points to the current received frame, I believe. Keeps these numbers lined up with the current ACK or received frame. An ACK is sent to represent that all frames with smaller sequence numbers are well received. If error happens, receiver holds ACK till the frame of sequence ACK is received. For example, firstly, frames 1, 2, and 3 are sent and frame 1 is received, ACK 1 is returned, frame 2 is lost, and frame 3 is received. Therefore, the receiver sets this and it waits. And it will not send ACK 3, I believe. Sender retransmits frame 2 and returns ACK 3. So this ACK 3, you see it returns ACK 3 when it's received frame 2. It already received 3, but never sent the ACK for 3. So sending this is what's known as a cumulative ACK. It's a method you can choose to implement if you so desire. But since it said this guarantees that we're using cumulative ACK protocol, which means you get to save precious ruler usage on drawing a line, because it means you get to send 1 ACK back for a brick of received frames if there was a transmission error. And this indicates that both of the frames that it was waiting for have been correctly received at that time. So now we have some questions. So ACK 3 and frame 5 are lost in their first retransmission attempt. So we have infinite bandwidth, so we don't care about that. That's easy. The sender will transmit 1 frame every 4th of an RTT. So that's going to be useful because he gives us little increment lines, so we can easily line this number up. And then a bunch of instantaneous transmission, and the sender can only perform 1 transmission per unit time of the RTT. A frame experiencing no delay is received at half of an RTT. So, one-way send time. And then after transmission starts and the processing time is 0. So all this stuff, just prerequisites to make sure our lines are pretty. And then we have at a specific time, frames or ACKs are received and processed instantly before transmission decision occurs. Receiver receives a frame and then sends the ACK if required. This if required thing is another way to tell you that we're using cumulative ACK protocol here. Sender receives an ACK and then determines if a timeout has occurred. So if it doesn't receive an ACK, it's going to wait however long the timeout, which what do we know? The timeout is 2 RTT here. And then it'll determine the next frame to transmit, assuming it's received an ACK. And then we have the timing diagram, which is what we'll probably have to fill out after we answer some questions. Clear those. All right. So the first things first is, at what time does the first timeout occur? So we can go down this timing diagram. And it said that ACK 3 and frame 5 are lost. So it's asking for first timeout. So what we know here is these are the only 2 errors that have occurred in this system. So the error that has occurred first is ACK 3 was lost. So we know that this system takes 1/4 of an RTT. Right? Is it a fourth of an RTT to transmit? No, it's half of an RTT for a full transmission across. So what does that mean for our funny little lines? Well, that means starting at time 0, frame 1 is received at this point right here, which is 1/2 RTT. So this is your starting point. So you draw a pretty little line that does that. And then of course, for your receive, it takes another half RTT. So your line goes to 1. So we saw that the ACK of 3 was the problem. So this was 1. This is going to be 2 should not go there. Let's undo that. 2 should go to the next one down, which is then received by the next one down here. And this is 3. So 3, the frame is received successfully, but the ACK is lost in transmission. It should have gone here. So the ACK that should have been received is not received. So now we have to wait the RTT time. So we are currently standing at 1.5 RTT. So we will go down, and the timeout time was declared to be 2 RTT. So we wait 2 whole RTT, bringing us to this time, which is 3.5 RTT. I believe. Or is it wrong? Let's see. Oh, it's going to come with us. What's this 4th? That's fine. Hmm.
I believe the timeout time would be after it would start after it's been transmitted. You don't add.
Yeah, that's there it is. That's probably it. You're right. So instead, the timeout time begins here. Hmm. Is it? So in his solutions, he claims it is three RTT plus a fourth of an RTT. So he says it should occur here. Yeah. He says it occurs here. That is still not drawing here. So this is where he says first one occurs. This is correct. It should, third frame should be received here. So this is frame 3 is received at RTT1. Third frame is received at RTT1, and then acknowledgement 3 is lost. So, okay, so he declares that the timeout starts at this point, which is the ACK, the last received ACK, which would be ACK 2. So I guess that's the notation we're working with here. So if this is ACK 2, that means the rule for this is going to be that timeout period begins after last received ACK. So if it starts at 1.25 RTT, right here is where ACK 2 is received. When you go up to RTT from there, because you never received ACK 3, you end up at 3.25 RTT. So that's the convention that he wants us to use. At last received ACK, your timeout period begins. So that's a good little piece of information to keep in your heads. Now, the thing is, we received everything. So where is ACK 1? ACK 1 is here. So ACK 1 is here, which means we got to go over to this, which means down to 1.5 is frame 4. And that goes down over to 2 is where frame 4 is received, the ACK of it. And then that means over here, which is ACK 2, we go this way and go, that's this one. Okay, we're gonna undo that and go to this. This is frame 5. Now it says frame 5 is lost to transmission, so we'll just give that an X. So now we have to time when frame 5's is lost. So let's make sure that's the question. First timeout. What are inside the sending window at time instant 5 RTT? So that's the next thing we'll have to calculate. So we'll have to go through the whole thing there. And it says, what is the seek num to ACK at time instant 4? So time instant 5. So let's bring this back down. So we got to go through this. So this happens, there's going to be a retransmission attempt eventually because we got to go through and we got to have to retransmit frame 3 at one point, or we're going to have to wait for a cumulative ACK coming from the next one, which means that our cumulative ACK occurs here because this is ACK 4. Remember, we lost ACK 3, but ACKs don't matter that much because the receiver received it. So on next ACK received, this receiver or this sender would realize, okay, if it's semi ACK 4, then that means it did actually successfully receive frame 3 because that's how the cumulative ACK protocol works. So there's no need to retransmit frame 3 because only the ACK was lost. The frame itself was successfully received. Now we are going to have to do a retransmit on 5 eventually. So we sent 5, it failed. Now we're now down here is the lowest point, which means the next thing to happen is from 2 to 2.5 is going to be frame 6. So we are at F6 now, followed by F7. Now, you notice that there's no ACKs for either of these. And the reasoning behind that is because frame 5 was lost. So no ACKs will be sent back, which means at the end, eventually, when 5 is successfully retransmitted, frame 7's ACK will be sent back to confirm that 5, 6, and 7 were all successfully received. Well, where was the last ACK received? The last ACK received after frame 5's failing was ACK 4. So timeout begins at 2 RTT, which means go down 2, down to 4 RTT, oof, down to 4 RTT, I said draw, is where we will actually go for the retransmission. Oh wait, no, that's not proper, is it? Now, why did they do it this way? That's interesting. All right, let's see. Act 4 is received here. Act 4 acted cumulatively. And then frame 6 is transmitted, easy. Now here he says that the timeout started after Act 4 instead. No. He says TO5. Okay, so he says that the timeout for 5 begins here at Act 2. No, that's right. It begins at Act 2 because that's where 5 was sent from, because this is frame 5 and it was lost. So starting from Act 2, we go from 1.25 up to 3.25 down here, which is where we finally get to retransmit 5, which means it is received at 4.75 or 3.75 RTT. So this is the successor received frame 5, which is then sent back and received at 4.25 RTT. What number ACK is this? This is ACK 7 because of the cumulative protocol. So ACK 7 is received because 5, 6, and 7 were the ones that we were waiting on confirmation for. So we're good there. And then going down from there, it looks like we just continue until we continue down through this figure until we run out of space. So on his figure, that ends up with him receiving at the last possible increment, ACK 10. But the question he was asking here is, what are inside sending window, which would be the frame numbers at time instant 5 RTT. So we need to move down to 5 RTT. So that actually is like all the way at the bottom. So for him, it looks like it would be, yeah, okay. By that, the stuff that's in the frame window is 8, 9, and 10. So I can't show it all in here because of the drawing, but let's keep that in my mind. Go down here. F5 was received. Mouse. F5 was received from here to here. So we'll continue from F5. F5 is received here. ACK is received here, and this is ACK 7. Now, there are no more transmission errors from this point on. It looks like he made a mistake in his solution and wrote that frame 7 is retransmitted, or frame 6 is retransmitted, even though it was successfully received. So it shouldn't have to be retransmitted. So I think, but frame 7 is also there. So I don't know why he drew this. It's a little odd because ACK 7 is received here and then frame 8 is sent. Because then ACK 7 is received again. Here, I'll show you what this looks like. It's a little wacky. Oh, you can see both of the, oh boy, I'm drawing everywhere. We're just gonna undo it all. Oh boy. There we go. So here's how he's got this guy. Now we're down here. And this is where ACK 7 was just received. And you see he transmits frame 6 again and then receives ACK 7 again. But frame 6 and 7 were successfully received. Frame 5 failed transmission. So by the cumulative protocol, this ACK 7 should nullify the need to do 6 and 7 again.
I think it's because it's the timeout time for F6 occurs before it receives X7.
Yeah, that's probably it. Yeah. It's keeping it. Yeah, that should be it. So he still had to do this, which is a waste of resources, but it was required by the protocol. Well, even then, so there's over there. So this is ended finally. And now from here, we go to F8, F9, then F9, spits out A9 and F10, A9. So the question was, what is inside the sending window at time instant 5 RTT? So you just come down here and you look what is being sent at this time. So you saw that frame 9 was received. So because the window size is 3, frame 9 means that 8, 9, and 10 is what's currently being sent and received around. So that's what's within the window. So the answer as seen here is literally 8, 9, and 10. And then it says, what is the seek num to act at time instant for RTT? So you go to for RTT right here, and it should go, yeah, because it just had received A7. F6 was retransmitted, but because Act 7 was what was sent, that means frame 8 is currently on transmission. So for RTT, why is it 8? That's interesting. We have 4 here because F3 was last received. A4 was received, so 5 was failed, so it's pointing to 5. So nothing changes, points to 5 still. Sends 5 A7. So A7 was received, so it points to 8. Because frame 5 was sent. So it's just whatever frame it's waiting on. Because 6 and 7 have already been received. 5 was just received here. So now at 4 RTT, the frame it's looking for is the next frame that it's yet to receive, which means frame 8. And then down here, we did 6 again because of the timeout period. 8 is sent, 9 is sent, 10 is sent. So 9 was received at 5 RTT, which means it is now 10 that is waiting on for the seek to act or seek num to act. So that's time instant 5. That's why 4 RTT is for 8. I answered a little more than necessary there. Looks like he's got a bonus question here. Okay, I mean, I guess that's just free points. Anyone want to take a crack at that one? Unnecessary. All right. So that's the other quiz. So that's everything. That's the whole exam 1. So in my opinion, very straightforward. The only things I could see potentially changing about would be maybe instead of a CRC, we do an IP checksum. In my opinion, IP checksum is even easier because it's straight up addition. I could see that, but I have a sneaking suspicion he's going to have us do CRC because it's a more useful and widespread thing. Short answer vocab questions. These could easily change and really just be any vocab that we've discussed, any terminology, any definition, any comparison that we've discussed. So in order to prepare for any of these little short answer questions, I recommend just going back through either the Panopto videos or his slides. Probably his slides are best. And just on those slides where he's defining terms, go through and read all of that stuff for yourself to make sure you're familiar with all the possible short answer questions you could receive. Just being generally aware of the vocab is probably good enough. Timing is interesting. So we use Manchester here, but we're aware of several different methods of timing, non-return to 0, Manchester encoding, all these different timings. So I'd probably go back through that PowerPoint and look at the timing diagrams to make sure you know what corresponds to a 1 and a 0 in each of those encoding schemes. Because while he might probably just give us Manchester again, doesn't mean he has to. He could give us any of them, and we're still expected to understand them. Similarly here, we have HDLC. So really all this stuff here, all these little 2-pointer questions are just things that we learned early on in the class. Like we learned 6 or 7 methods of, encoding data in one class period, and everyone probably forgot about it. But it's going to pop up as these little 2-pointer questions. And these things really aren't hard, and it's not really that difficult to keep them straight in your head. So I recommend going back and looking at them to make sure you've got that solid, because it's annoying to lose points where you easily could have gotten points. Similar to this bit destuffing thing, this is such an easy question as long as you understand what this, bit destuffing and bit stuffing does and how it operates, and you're chilling, right? And then this is just parity, like parity. He could give us double bit parity, quad bit parity. In fact, we spent a lot of time on the 4-bit parity, right? With the geometric schema for that. So that could pop up even, make it a little more complex, but it's important to understand how parity works. The question yet again, relatively simple. You just make sure that the numbers match up and everything. But in this case, it's an error and the data would have to be the same. This didn't happen. Now we're going to go over to the other exam because there are questions there that are very important, particularly VCI, which is a big part of the second exam. And we all just did a big old homework assignment on it. So, that's also pretty important. So you can see again, both exams have CRC. So we're not going to look at this weird version. We're just going to look at the solution because for some reason it was done on paper, and that's a lot easier to understand than this monstrosity. So we'll go with that. So yet again, we see CRC, very simple CRC, standard stuff. You map this in. So least significant bit is a 1. X to the first is not present, so it is a 0. X to the second is present, so it is a 1. And because x to the second is the highest order term, that means our remainder is 2 digits long, and easy peasy, it is 2 digits long. Nice. Now we have a checksum here. So if you're asked to derive the 3-bit checksum code for M, what is your answer? So he's talking about we use 8-bit checksum here. All right, so here's our message. Lucky for us, he used 3 bits and it's 3 bits long. So you can see the simple thing here. He just adds this to this, which is 101 plus 0, 1, 1. And this just produces 1, 0, 1, 0. Then you take the 1's complement of it, which would produce. Did you take the 1's complement? No, sorry, that's not what he did. I messed that up. This is how that happens. When you have carries, you take the carry and just slap it onto the end in an addition, which would turn this 1, 0, 1, 0 into 0, 1, 1. And then you take the 1's complement, which is as simple as turning 0s to 1s and 1s to 0s. And now you have this. So that would be the checksum of your message. Really simple. As mentioned, he could give us a checksum. He could give us a hard checksum. He could give us an easy one like this. There's no way to tell for sure, but it's good to be familiar with all of those things. So for reviews for checksum, it's probably perfect to just go look over your homework assignment. That checksum problem he gave us, the 8-bit checksum, really just hammers home what that's all you have to do for it. Nothing too crazy. Doesn't even look like it. That's interesting. If you're asked to derive the one-dimensional even parity code for M, what is your answer? So even parity. So what are we adding on to make it even parity? Count the 1s. We have 5 1s. Therefore, the parity bit is a 1 to make it 6 1s. That's all that question is. For a second, I thought he didn't answer it, but I guess that's really all I was looking for. Just a line on the paper. He could have done that one by accident, honestly. So 2, answer the following short answers. This is a big chunk of problems. See, look, all these little vocab questions, right? Like these are the kind of things that you might have just been, zoned out in class and you miss, which layer is which in the OSI model, right? You got to be able to remember these things so you don't lose out on those easy points. So which layers the OSI model does HTTP protocol begin to? The application layer. Why is it the application layer, you ask? Well, let me pull up like a website or something. Boom, look at that. Okay, let's just go to like Canvas. I want to see the lock. There it is. Boom. That's HTTPS. I can see it. This is an application. Boom. It is application layer. Easy. What is that? Hypertext transfer protocol? Is that what that stands for? I'm pretty sure that's the case. All right. Next question is, what are the 2 steps in 5-bit to 4-bit encoding? You map 4 bits to the 5 bits. Now, when I say map, you literally, there's just like a library or dictionary that you use as the map. It's just an explicit thing. There's no math being done. And then the second one is you just encode. Like this kind of stuff is just quick vocab that you'd get out of memorizing slides. Again, bit destuffing. So following bits are from the data payload field in the HDLC based frame. Please mark errored bits and stuff bits if there are any. So looking here, remember, you cannot have more than 5 contiguous zeros in HDLC or 5 contiguous 1s in HDLC. So boom, we have 5 1s here, and the next one was a 1. What does that mean? It means you slap a 0 on it. So there you go. You know that that's a stuffed bit. Now over here, here's our 5 contiguous 1s, and oh no, there's another 1. Therefore, that has to be an error. Otherwise, that wouldn't have happened. It would have been a stuffed bit, which is a 0. So that's all you had to do here. Very simple, very quick. No issues there. Why is the sliding window protocol advantageous over the stop and wait? Oh, it says it really easily here, but we can bring back the solution to the past one and look at it real quick. Sliding window beats the hell out of stop and wait, because if we were doing stop and wait, instead of transmitting frame 2 here, we would transmit frame 2 at 1 RTT instead, because we'd have to wait for ACK 1, which loses us a massive amount of throughput because we're not utilizing the bandwidth we have, right? It's a big problem. So easy. So this just says keep sending data while waiting for ACKs or better bandwidth utilization. Either of those answers, perfectly fine. How can hidden nodes be detected? And that's literally it. Request to send and clear to send. So I mentioned this earlier in the hidden node problem, but request to send, let's do the little ABC again. This is the simplest way to illustrate. So ABC, A's range is like so, C's range is like so, picture circles. Request to send, A wants to send to B. So to C, A was a little bit quicker than B or C, and it said, hey, I sent my RTS to B. B says, aight, homie, I'll let you send. And B does this big signal out, and that's your CTS signal. What does CTS mean? Well, C has not yet registered that it sent RTS in time, which means C realizes, hey, if the CTS was broadcasted before my message was received, that means someone else beat me to the punch. Therefore, I got to shut the hell up. And C is quiet. That's all that is. So this is a quick answer, but I'm sure you could answer this just as easily in a sentence, a figure, anything you want, right? As long as it is understandable to the grader. Consider the sliding rotor protocol runs over this 40-kilometer fiber link. It gives you the speed of light in the fiber, and it gives you the bandwidth, which is thick 1 gigabit. So it says, what is a suitable timeout value? So when you calculate timeout values, first you want to just calculate RTT, and then you got to multiply it by 2, because when we're using the sliding window protocol, we have to wait for the frame to be sent and the act to be received. If the timeout is shorter than this single contiguous period, which is 2 RTT, because 1 RTT to send, 1 RTT to receive, your timeout is, let's say, this length. Guess what happens? You send the frame, even if the act was on its way and there was no transmission error. That is obviously a waste of time and resources. So it's stupid. You want to make sure your timeout period is definitely above. So in this case, he just gives you the range, which is greater than or equal to. In my opinion, I'd probably cut out the equal to because delays exist, but even so, he'll take it, so he'll take it. So you just calculate RTT, multiply it by 2. There's your time. There's your timing. In fact, this exact question was on our homework. Or at least, probably not the exact question, but at least 0.4 milliseconds. Was it 0.4 milliseconds? Was that what the homework number was? Let me check. Pop, 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 pop. Yeah, the RTT was 0.4 milliseconds on homework 2 as well. So I don't know if they're the same problem, because the it didn't give us bandwidth for this one, but that's for this part anyways. So what is the maximum allowed sending window size? So this is about how many bits you can stuff in there, right? And this is our frame and the maximum window size to make the pipe full. So RTT times bandwidth. So we calculated RTT up here, which is 0.4 milliseconds. And the bandwidth is not 109, that is 10 to the 9th, which also happens to be, 1 gigabit, 1 billion bits, right? Or 1 billion bits per second. So let's look at the units here. RTT is just time, and bandwidth is bits per second, which means time canceled, and we're left with the unit of bits. Good way to check your answer. So this is 4 times 10 to the 5th. Bits is the pipe full number. When you multiply the RTT by times bandwidth, this is the quantity of bits to keep your pipe at 100% utilization. And then down here, your sending window size is then going to be your frame size, which is 4 kilobytes, or it's going to be your bits, 5 times 10, 4 times 10 to the 5th, divided by your frame, which sending window size is a unitless protocol, which means you're going to have bits divided by bits here. So all you got to do is look at the numbers he provides you, 4,000 bits, and your answer for the previous calculation is in bits. If you have a unitless system, then boom, 100. So your sending window size is 100 frames. That's a chunky sending window size. Luckily, we don't have to calculate anything about that. Scroll on down. What is this one? End-to-end, propagation delay, store and forward switch setting, queuing delays, bandwidth link, maximum frame size. All right, so this looks like just parameters of a network. That's always fun. Transmission time for the maximum size frame. So we were given maximum size frame is 5,000 bits. That's simple. So we need to look for a bits per second unit to produce a unit of time on the output. So we have 500 megabits. And as you can see here, 5,000 bits divided by 5,000 megabits per second yields time as your unit. So that you know that this is the proper calculation. It gives you the proper unit. And then of course, doing this math just yields 10 microseconds. No trick there, nothing too difficult. Then we have how long does it take to transmit a maximum size frame from one end of the network to the other? So you have to, as he says here, include the switch's transmission time, which is as stated to be 2.5. And it looks like there is a single switch in there. Yeah, nothing tricky. So we have the standard transmission time of 10 microseconds, propagation time calculated via the length divided by the speed of light, done right there. The queuing time of 2.5 microseconds plus another transmission time, because this switch is in the middle, which means the propagation delay introduced here from a frame occurs twice. So you got to make sure you know that, because our network looks like this. Sender to the switch, the receiver. Switch is in the dead middle, meaning any type of propagation delay due to transmission time occurs on both links. So that's why you get 10 twice, or TX1 and TX2. Sum all these up. That's an easy calculator problem, 27.5 microseconds, nothing tricky. Let me clear that. Now we have CSMA-CD is used on this network. So CSMA-CD would be a Ethernet network. So that's the first thing we get to learn from that. Using the answer is used on this network. Using the answer you find in part B, what is the minimum number of bits in a frame that can be used such that a transmitting node is guaranteed of detecting a collision? Well, part B is this. So this is the one-way transmission time. That's important to know because you did not consider. So this is a half RTT. It's one way. So an RTT is 2 times this. Or in this case, looks like they did some funny stuff for it. So RTT, so we have 2 times propagation plus Q plus transmit again. So doing that, so propagation is from speed of light along the link. So that looks like that worked out to be 5 microseconds plus Q time, which, as we know, is 2.5 microseconds. So this is 7.5 microseconds times 2 for RTT yields this. And then we have plus 10 for transmission again. So obviously this would be 15 plus 10 is 25 microseconds. Okay, that's fine. And then we have, interesting thing is why they use one transmit. I guess I'll have to go with that answer then. And then, don't need that. And then it goes down for the minimum frame size is just going to be your RTT times your bandwidth again, because you want it in bits. So you need a unit of time times a unit of bits per second to yield a unit of bits. So you take the thing, you take the time yielded from here, which is 25 microseconds, times the bandwidth given all the way at the top, being 500 megabits, yields you 12,500 bits. Now you could give that in bytes, you could give it in nipples. I don't think he cares. It's just up to you. So leaving it in bits is the simplest. Now, here's the thing that did not occur on the other exam, but did occur on our homework, and I almost can guarantee you that it will appear on our exam tomorrow. This would be VCI, virtual circuit switching, or virtual, yeah, was it virtual circuit? Yeah, I don't know, I said that wrong. VCI is virtual circuit identifiers. Let's go with this. Consider the following virtual circuit network. The network already has some existing connections, which are not shown. In light of it, some virtual circuit identifiers have been allocated. Note that the network follows the rule that the VCI assignment always picks the lowest available value. The following table shows that the next VCI to use for some interfaces that are of interest. So this is the mythical VCI table for us. So it can give you your switch and the incoming interface and then tell you which VCI is to be marked for that. So we have a network, the exact same network that was on our homework, or at least the exact same image of it. And then we have 3 questions, A to J, B to E, and E to A. So quick thing to do is you're going to want to draw lines. So starting with A to J, we are going here. Boom. So we hit switch 1, 2, and 3. And we go through link 2, 1, 3, 0, 1, and 0, and 1 for question 1. So Let us clear that again. Go down here. So this is, please fill out the following table. If a connection does not pass that switch, please fill in NA. A sample work has been done for switch 1, and you can use it to start. Hint, remember the chain effect. That is the outgoing VCI of a switch equal the incoming VCI of another switch. So let's see. So this is for switch 1. Is this for A? What? No, this might be worth looking at because this seems like it's rather interesting in how it's being done. So simply decoding how he wants us to fill out these is going to be interesting. Actually, never mind. Let's think. Connection 1, 2, 3 probably refers to A to J, B to E, E to A. So that's how that works. So for each of these, we mark it for each switch. So for A to J, we hit 2 to 1. So let's think. So it said 1 was filled out for us. Good, done for switch 1. So for connection 2, does it ever hit switch 1? B to E? B to E never hit switch 1. Hence, switch 1, this box is all NAs for connection 2. So for this one, connection 1, we'll work this one out. So it says 2 is the incoming interface, 3 outgoing interface, 1 outgoing VCI 4. All right. So let's think. A is 2 being your incoming interface. Therefore, going up to here, 2, switch 1, incoming interface 2, VCI to use is 3. Which means the incoming VCI is 3. The outgoing interface of 1, because we have to go over here to get over to J, on switch 1 yields us, that went too far, on switch 1, oh wait, it should just be 0, right? No, it's gonna be 3, which means, no, it's gonna be 4. I think it's because it's headed to 3. I think we only deal in incoming interfaces here. So it went into 2, and then it went to 3 on switch 2. So we go to switch 2 to incoming 3 and see that it is 4. Come down here. Therefore, the outgoing interface of 1 is going to need to use the outgoing VCI of 4 because that's what's going to be received on the incoming interface of 2. Of 3, 2, which yields 4. And so on and so forth. You follow that same pattern. Does anybody have questions on this stuff? Because this one's definitely the most confusing topic, if anything. No questions, no issues. Let me bonk. All right, good. There's no problems. We'll just look over to the next 2 switches then. So it looks like you only gave enough of them to give partial chains, because in reality here, we went from A, so the incoming is 2. So you just go to switch 1, 2, 3. So you use the VCI of 3 as mentioned here. And then your outgoing interface of 1 is headed to the ingoing interface of 3, 2. Go down to switch 2, 3, 4. So you did that. Now, of course, this doesn't automatically route you and finish you off over here, but it didn't give enough length, didn't give enough space. Oh wait, no, this is on a switch by switch basis. All right, now we go over here. We're switch 2. Now the interface of switch 2 that it has been received on is 3. So the incoming interface is 3 and the VCI is 4. Why is that? Because it needs to match. As you can see, these arrows that are drawn prove that exact process. The outgoing must be equal to the incoming between interfaces, because it was going here. It was labeled 4 here, and now it's headed over to 0, I believe. Or no, that's just what it is. It's in on 3, which means it's 4. And its outgoing interface of 0 goes to 0. So let's go to switch 2, 0. Next VCI to use is 2, it says, which is wacky doodle. But I think it's pre-allocated already, which is what that means. Because it's outgoing to outgoing is 0. And then the next level for 1 is down at switch 3. So obviously the incoming interface is 0 to 0. So it comes in 0, and it was previously 0 as the outgoing VCI from switch 2. So that means switch 3 has an incoming VCI of 0. And then the final routing is it needs to hit host J through 1. So we go up here to switch 3, 1, meaning the next VCI to use is 1. Therefore, the final VCI to use outgoing interface is 1, the outgoing VCI is 2. So why is that? Let me see that. Switch 3 is 1 to 1. Why'd you use 2, man? Was it allocated already? Lowest available value. Ah, I see why. So we used 2. No, we used 3. We used 4. 4 moved there. We used 0. We used 0. So we had to use 2. Because that was the lowest. I went too far. And that's that. So that same chain of logic is, I guess this is how it'll be done on the exam. That's interesting. So you just gotta keep track of where everything goes. And it looks like these arrows definitely help between questions. So this is extremely similar to the one that we have already done. So I'll leave that one be. But this big brick of text looks very scary. But in reality, a lot of it is just to make sure people can't argue why their answer was right or wrong per se. It's just very specifically setting up the conditions of the system. So that's all that is, nothing too crazy. So that's fine. So that's that. We've done about an hour so far. It's not necessary to keep pushing it longer unless there's any questions. So any parting thoughts, questions, or concerns about topics that may not have been on these practice exams, but you want some clarification on before we close out and I upload it?
How likely do you think it is that we're going to need to memorize all the OSI layers?
I mean, I would just have it. It's really not that tricky, honestly. Like 1 through 7. The
Well-
thing is, the odds aren't super high because there's a lot of vocabulary-esque questions he could ask. And the OSI questions make up a smaller part of it. He's more likely to ask, something like one of
Yeah.
these, like encoding stuff, like from the last one, the HDLC stuff, the 5 to 4, 8 to 10. It could also be like the Manchester one. So
I mean, more specifically, like 2A there, like,
yeah,
am I
like
going to
that.
have to know what HTTP or URL or whatever the other one was that's an application? Is there a chance I'm going to need to know some other kind of stuff and what layer
There's
it's in?
definitely a chance. So like he could ask, what layer in the OSI model does a repeater belong to? It's a layer 1 device because all that thing does is deal with just signals. It has no memory. It just it amplifies and passes. It does nothing, no routing. It just sends it through. So now he wouldn't ask questions about stuff we've not discussed at all. I know for a fact we've talked about HTTP and where it is. You probably, like in the OSI model slides itself,
Yeah, I
probably
see
had
that in my
examples.
notes.
Yeah, so he probably has examples, right? But I doubt if there's going to be a question, it's either going to be like this one, the application layer, the 7th layer, which in reality, if you just logic your way through it, if you're even remotely familiar with what the example, in this case HTTP is, you'd know immediately that's got to be application because it directly impacts what I see on my screen, right?
Yeah.
It's got nothing to do with routing. All the data has already been, it's on your device by the time HTTP even begins to happen, right? Like it's already there. So it's ready. So I would say 7th layer and then 1st through 3rd layer are the most important ones to nail down your examples and understanding of. We've been dealing almost exclusively in 1st through 3rd. What is it? Physical layer, IP layer, then.
Yeah, that makes sense. I don't remember us going over anything in the session layer.
Yeah, no, like all that stuff is definitely off the table. I wouldn't worry about that. I'd worry about examples of 7th layer and examples of 1st, 2nd, and 3rd layer.
All right.
Yeah, so that's good. So Yeah, that's how it would be. So what is it? First layer, you'd have like repeaters. Second layer, you'd have what is a router second layer, and then a hub is third layer.
I got
A router's layer.
switch is second layer and router is third.
Okay, flip them. Yeah. So you have first layer has no bearing on direction. First layer just passes it along to the next link. It has no concept of routing. Second layer, you could have more wires, more complexity. You can route stuff, move stuff around. You can have addresses, right? And then third layer is where second layer is switching. So you can have a very basic level of routing. And then the router is the more advanced level at third to send it across like the actual network once you've reached your target. Even so, just memorizing examples of that will probably cover you for your 2-pointer questions.
All right.
So that should be fine. I still advise probably like really looking over VCI stuff, because how much was that VCI question worth on this? This is a 50-point exam, and the VCI question was worth 10 of them. So we have a 20-point exam, so you can see the VCI question being worth whatever 10% of 20 is. So that'd just be 2 point. No, that doesn't make sense. No, it's 20%. So it'd be 4 points, right?
I don't know why he makes his stuff worth so few points.
And in reality, it just like it simplifies. If you're willing to work in the decimal domain of giving people like 1.9s and stuff, then you're fine. It's just scaling it to be less points overall.
It like partial credit wise, it just doesn't make as much sense to me.
Yeah. As I mentioned, if you're willing to work in decimal points, then it's fine. Like I got like a 1.9 on my homework one.
I did too.
Yeah, so it's like it's just how it is. No, it's not too bad. I don't think it's the worst thing in the world. It's his preference. He can do what he wants, I suppose. But yeah, VCI is big, and sending window protocol is big. Those two things take up a majority of the points for sure. And
Wait,
CRC.
sending with no protocol?
Sending window protocol.
Oh, sending window. You mean sliding?
Sliding. Sorry about that. Sliding window protocol. Sorry, would be, as we saw, there are commonalities between these two exams. One being CRC. That's probably definitely going to be there. Another one being the sliding window protocol questions, of which both of them in high amounts of complexity have occurred, right?
Yeah.
And
I'm
then,
pretty good on all of those three. The things that I'm going to struggle with is the 2-pointer questions.
Little vocab. Yeah, and then you'll have like this stuff, which I like to call network parameter questions, things where you're just doing math to figure out timing and everything. That's not too bad. Just keep your units straight. Nothing too wild there. And then this is another parameter question. And then yet again, these are vocab stuff. So vocab stuff's big. So just make sure you have all of that, all your ducks in a row with regards to that, and you should be chilling.
All right.
So whatever slides necessary to look over, just give them a quick peruse. If you want to really remember it, just like pull out a blank piece of paper and just write down all the vocab you think is pertinent and just copy it 1 or 2 times, and you'll be good. You won't forget it.
All right.
That's an easy way to, if you ever need to cram and don't care about remembering the information for very long, just writing it down 3 times over is a really easy way to get it in there.
All right.
Yeah, so that's good. Oh, that's that. Bonk. Yeah. All right. Any other questions, concerns, mortal fears?
None for me.
Phobias of clowns, perhaps? Anyone remember that like 3-4 month period where there were just people dressed up as clowns chasing people around?
Yeah, those guys better be glad that I did not own a gun.
Those are the good old days. Those are the good old days when you could dress up as a clown and just like vibe. I had to throw my clown suit away, man. Unfortunate. All right, well, that's that. So I'm gonna end it here, and I'll just go upload it. If anyone thinks of any questions before exam, if you just send them to the Discord. Phoebe's out here or smacking people with the clown mask. Yeah, there's indeed no point in being a clown if you have to wear a mask. You should definitely just you gotta have the makeup. You gotta be able to honk.
You could get a mask and like hot glue a clown nose to it.
Yeah, I suppose works out.
Or since the nose like covers your nose, you can use it as like a partial mask and then just wear the mask over your mouth and then still wear the nose.
It could work. Yeah. Anybody ever just look in the Discord and just see the sheer like spread of all the names people have and just wonder to yourself, where do they come up with some of this?
Yeah.
One of my favorites is severe artism. That's a good one.
I haven't seen that one.
They're currently playing Minecraft. It also
Oh,
seems,
yeah, that's the dude that made this.
yeah, exactly. Yeah, even so, it'd be like that. All right, I'm gonna end it here and I'm gonna upload it. If you ask questions to the Discord, I'm sure I or someone else will answer it in the help tab or in the general tab, whatever one wants to do.
All right.
Dinner time now. I gotta go eat something.
Thank you.
Yep, no problem.
Thanks, Ethan.
Yep, see ya.
Good night.
You
Bye.
too. Stop.